The website Bionichaos focuses on exploring biomedical data science and engineering. It offers interactive tools and insights into data visualization and signal processing. Key topics include EEG electrode positions, seizure detection, EEG data handling, and integrating AI and machine learning for biomedical analysis. The site also features guides on interfacing with hardware using Python, creating interactive applications, and visualizing EEG data. For more information, visit Bionichaos/. The Bionichaos website offers a range of tools and applications designed to explore and visualize biomedical data, particularly focusing on EEG and ECG signals. 1. Vision Impairment Simulator. This tool provides a real-time experience of various vision impairments, including myopia, hyperopia, cataracts, glaucoma, and color vision deficiencies. It allows users to adjust parameters like blur, brightness, contrast sensitivity, peripheral vision loss, and color saturation to simulate these conditions, making it useful for educational and awareness purposes. 12 source. 2. CardioQuest ECG Scoring Game, an interactive game that tests users' ability to identify abnormal ECG patterns. It generates different ECG waveforms, including variations and abnormalities, challenging users to recognize and score these patterns. 13 source. 3. EEG Data Visualization. This application uses Plotly for interactive plots, allowing users to visualize and analyze EEG data. It features zooming, panning, and dynamic plot updates based on user input, making it easy to explore specific time intervals or patterns within the data source. 4. ECG Synthetic Signal Generator. This tool emulates various ECG waveforms with detailed parameter customization. Users can simulate normal and abnormal ECG signals by adjusting parameters like BPM, noise levels, and voltage, providing a dynamic platform for educational and research purposes. 50 source. 5. ECG Waveform Feature Extractor, a web-based tool designed to visualize ECG data, allowing users to adjust parameters such as duration and heart rate. The tool generates ECG plots with marked features, facilitating easy identification and analysis of cardiac electrical activity. 60 source. 6. ECG Waveform Visualization. This project aims to develop an interactive tool for simulating and visualizing ECG waveforms. It quantifies key components of the ECG signal and overlays variations in the QRS complex, providing educational insights into the characteristics of ECG signals. 7. Cochlear Simulator. This simulator visualizes how cochlear implants stimulate the auditory nerve by dynamically changing the color of electrodes based on audio input. Users can adjust parameters such as the number of electrodes and filter settings, providing a hands-on understanding of cochlear implant functionality. 18 source. 8. Synthetic EEG Signal Generator. This tool generates synthetic EEG signals for testing and educational purposes. It uses Flask, Plotly, and JavaScript to create interactive visualizations and allows users to adjust parameters to simulate different EEG conditions. Source. 9. EEG to Music. This unique tool converts EEG data into music, offering both visual and auditory experiences. Users can interact with EEG data, apply filters, and listen to how different brainwave patterns sound, providing a novel approach to EEG analysis. 20 source. For more detailed information and to explore these tools, visit Bionichaos/bionichaos.com/. Here are additional details about the various tools and applications available on Bionichaos. 10. About Bionichaos. The platform's vision is to create an open, user friendly environment that supports various signal processing topics, aiming to democratize biomedical data processing. Developed by Yuri Benno, Bionichaos focuses on providing accessible tools for understanding and analyzing biomedical data. 11 source. 11. EEG synthetic signal generator. This tool generates synthetic EEG signals using the fast Fourier transform (FFT) algorithm to convert time domain signals into the frequency domain. It helps in research, testing signal processing algorithms, and educational purposes by simulating brain activity and analyzing EEG signals. 19 source. 12. EEG to music. This tool allows users to explore EEG data through interactive graphs and by converting the data into music. Users can select specific channels, apply filters, and listen to the music generated from EEG waveforms, providing a unique way to analyze brain activity. 20 source. 13. Cochlear simulator. This simulator visualizes how cochlear implants stimulate the auditory nerve by lighting up electrodes based on the frequency content of an audio signal. It offers controls to adjust the number of electrodes and filter settings, demonstrating the functionality of cochlear implants in real time. 18 source. 14. ECG waveform visualization. This project aims to create an interactive tool for simulating and visualizing ECG waveforms. It helps users understand the key components of ECG signals and the variations in the QRS complex through an engaging and educational interface. 15. EEG data visualization. This application uses Plotly for creating dynamic and interactive plots of EEG data, allowing users to zoom, pan, and explore specific time intervals or patterns within the data. It is designed to be user-friendly and adaptable to different environments. For tolerance source. 16. CardioQuest ECG scoring game. This interactive game challenges users to identify abnormal ECG patterns by generating various ECG waveforms. It provides an engaging way to learn about ECG signals and their variations. 13 source. 17. ECG synthetic signal generator. This tool simulates ECG signals with customizable parameters such as BPM, noise levels, and voltage. It is useful for educational and research purposes, offering insights into the effects of different conditions on ECG waveforms. 18. Vision impairment simulator. This tool allows users to experience various vision impairments by adjusting parameters like blur, brightness, contrast sensitivity, peripheral vision loss, and color saturation. It is designed for educational and awareness purposes. 12 source. 19. ECG waveform feature extractor. This web-based tool visualizes ECG data with customizable parameters like duration and heart rate. It generates ECG plots with marked features, aiding in the analysis and study of cardiac electrical activity. 16 source. For more information and to explore these tools, visit the Bionichaos website, bionics.com/. Here are additional details about the tools and applications available on Bionichaos. 20. Synthetic EEG signal generator. This generator creates synthetic EEG signals using Flask, Plotly, and JavaScript. It allows users to specify parameters like frequency range for different EEG bands, generating realistic EEG like data for research and educational purposes. The generator also calculates power spectra using the Welch method, enabling users to analyze signal characteristics. 19 source. 21. ECG waveform simulation and analysis. This project focuses on creating an interactive tool for simulating and visualizing ECG data. It uses plotly.js for data visualization and allows users to overlay variations in the QRS complex, providing insights into the key components of ECG signals. The goal is to enhance the understanding of ECG waveforms through an engaging and educational interface. 7 source. 22. EEG to music. This application transforms EEG data into both visual and auditory experiences, allowing users to explore brainwaves through interactive graphs and music. It offers features like auto volume and duration adjustments, customizable filters, and a channel selector to analyze different EEG components and their musical equivalents. 20S source. 23. Vision Impairment Simulator. Designed for educational and awareness purposes, this simulator offers a real-time experience of various vision impairments. It includes controls for adjusting blur, brightness, contrast sensitivity, peripheral vision loss, and color saturation, helping users understand the visual challenges faced by individuals with conditions like myopia, cataracts, and glaucoma. 12 source. 24. CardioQuest ECG scoring game. This game generates different ECG waveforms, including normal and abnormal patterns, challenging users to identify and score these variations. It serves as an interactive and engaging way to learn about ECG signals and their clinical significance. Source. 25. Data visualization. This application leverages Plotly for interactive and dynamic visualization of EEG data. Users can zoom, pan, and focus on specific time intervals or patterns, with the interface updating dynamically based on user input. It is designed to be intuitive and adaptable to various deployment environments. 14 source. 26. ECG synthetic signal generator, a tool for emulating various ECG waveforms with detailed parameter customization. It allows users to simulate normal and abnormal ECG signals by adjusting BPM, noise levels, voltage, and other parameters, providing a hands-on platform for educational and research applications. 15G source. 27. ECG waveform feature extractor. This tool visualizes ECG data and allows users to adjust parameters like duration and heart rate. The generated plots include marked features such as P, Q, R, S, and T peaks, facilitating the analysis and study of cardiac electrical activity. 16 source. 28. Cochlear simulator. This simulator visualizes how cochlear implants stimulate the auditory nerve based on audio input. It includes interactive controls for adjusting the number of electrodes and filter settings, demonstrating the functionality of cochlear implants in real time. 18 source. 29. ECG waveform visualization. A project aimed at developing an interactive tool for simulating and visualizing ECG waveforms. It focuses on enhancing understanding of ECG signals by quantifying key components and overlaying variations in the QRS complex. 17 source. For more information and to explore these tools, visit the Bionichaos website. Bionichaos.com/. Your script is well structured and designed for creating an XML sitemap while logging errors and missing links. However, the code snippet provided is extensive and already handles various aspects of sitemap creation and error logging. Here are some key points and potential improvements. 1. Error handling. The script logs different types of errors, such as client errors, timeouts, and unexpected errors. This is essential for debugging and improving the robustness of the web scraping process. 2. Fetching page details. The fetch page details function is comprehensive, checking for error indicators, page text length, and the presence of essential HTML elements, title and description. This ensures that only valid pages are included in the sitemap. 3. Logging errors. The log error function is used consistently to record any issues encountered during the fetching of page details. This helps in maintaining a clear record of any problems. 4. Creating sitemap. The create sitemap function generates the XML sitemap by iterating through directories and fetching page details asynchronously. Sorting the directories by last modification date ensures the most recent changes are reflected in the sitemap. 5. Fetching landing page links. The fetch landing page links function extracts all links from the landing page, which is useful for comparing against the sitemap to identify any missing links. Potential improvements. 1. Concurrency. The use of asyncio.create task and handling of tasks in create sitemap is appropriate for asynchronous processing. However, you might want to add a limit to the number of concurrent tasks to avoid overwhelming the server or running into resource limits. 2. Additional error checking. While the script checks for various error indicators, you could extend this to include more specific checks for other types of common errors or issues in web pages. 3. Logging and reporting. Enhance logging by including more detailed information, such as response times and sizes of pages fetched. This can help identify performance bottlenecks or unusually large pages. 4. Configuration. Externalize configuration values, e.g. ignored directories, base URL, and directory paths into a separate configuration file or environment variables to make the script more flexible and easier to maintain. 5. HTML parsing. The script currently uses Beautiful Soup to parse HTML. While this is a good choice, you might consider using other libraries like LXML for faster parsing if performance becomes an issue. 6. Documentation. Add more comments and documentation within the script to explain the purpose and functionality of each section. This will make it easier for others or your future self to understand and modify the code. 7. Error snippet logging. The snippet logging in case of errors is a great idea. Ensure that sensitive information is not inadvertently logged, especially if the pages might contain private or sensitive data. 8. Unit tests. Consider writing unit tests for your functions to ensure they handle various edge cases correctly. This is particularly useful for functions that fetch and process web pages. Here's a small enhancement to handle concurrency better. Python async def create sitemap, base URL, path, max concurrent tasks 10. Sitemap equals XML version 1.0 and sitemap equals URL set xml.sitemaps.org/hema sitemap. Directories
Getting stuck on the random business. Probably have to start a new chat. This is really interesting. Yeah, the table doesn't fit anywhere.
To manually check each link one by one, you can follow these steps. 1. Create a checklist. Use a spreadsheet or a text document to list each URL along with its description and title. 2. Visit each link. Open each URL in a web browser to verify the content and ensure that it matches the description and title provided in the sitemap. 3. Check for errors. Look for any issues such as broken links, incorrect content, or missing elements. 4. Log issues. Note any discrepancies or issues you find so they can be corrected. Here's a structured approach you can use for the process. CHAP step-by-step checklist. 1. Create a checklist. You can use the following format to create your checklist in a spreadsheet or text document: URL, last modified, description, title, status, notes. 2000 Bionichaos.com. Explore 24085. Trutthint. Datasets, software tools, hardware devices. Bionichaos.com/resources. 224, a curated collection of EEG datasets, publications, software tools, hardware devices, and APIs for brainwave analysis. EEG datasets and resources. Not checked. hbionichaos.com/I2 2024-0804. Review 16 channels, 8 from each hemisphere, of intracranial EEG, IEEG, sampled at 400 Hz with epileptic seizures recorded using the NeuroVista implant. Bionichaos.com/gait analysis. Step into the fascinating world of gait analysis with our dynamic and interactive web application. This engaging tool brings the science of walking patterns to life. Gait analysis application not checked. Bionichaos.com seizure foods 2024-0803. Seizure foods.
Okay, can you go over the columns in this table? We eventually would like to turn the entire XML in a table like this. I'll share the whole XML with you shortly. Okay, don't generate the table yet. Just the full sentences text response.
Sure, let's go over the columns in detail. URL column. The URL column lists the web addresses of each page that needs to be reviewed. This corresponds to the loc element in the XML sitemap. For example, bionichaos.com/resources would be an entry in this column. Last modified column. The last modified column records the date when the content on each page was last updated. This information is taken from the last mod element in the XML sitemap. For instance, a date like 2024-085 indicates when the content was last modified. Description. Column. The description column provides a brief summary of the page content. This comes from the description element in the XML sitemap. An example description might be, explore a curated collection of EEG datasets, publications, software tools, hardware devices, and APIs for brainwave analysis. Title column. The title column indicates the title of the web page, which helps quickly. Based on the XML sitemap you've provided, you can transform each entry into a row in a table for manual review. Below, I'll explain how each element from the XML corresponds to a column.
A change of mind. Can we add checked, non-checked status entry into the XML itself, and also add a notes entry that will include what needs to be done? Can you, without any code, summarize this conversation in continuous sentences, full paragraphs, no code?
In this conversation, we started by discussing the need to review and transform the XML sitemap data from the Bionichaos website into a structured format. The goal was to convert the XML data into a table that could be manually checked and edited. Initially, we outlined the columns for the table, which included URL, last modified, description, title, status, and notes. Each column corresponds to specific elements in the XML, except for status and notes, which were intended for manual tracking and observations. After reviewing the XML structure, it was suggested to transform the XML data into a JSON file for easier editing and viewing as a table. A Python script was provided to parse the XML, convert it into JSON, and save it as a file. This JSON file could then be loaded into a web application or tool that supports JSON editing. However, there was a change of plan, and it was decided to incorporate the status and notes entries directly into the XML itself. This would allow tracking the review status and any observations directly within the XML file. A Python script was proposed to parse the existing XML, add the new status and notes elements, and save the updated XML structure. The final XML structure would include these additional elements for each URL entry, making it easier to manage the review process without switching formats. Throughout the conversation, the focus was on ensuring that the XML data could be easily reviewed, edited, and maintained, with a clear structure for tracking the status and notes of each URL entry. This approach ensures that all necessary information is contained within a single, well-organized XML file. To modify the provided script so that it adds status and notes elements to the XML, I'll integrate these new elements into the create sitemap function. Here's the updated version of your script with the necessary changes. Python import OS, import datetime, import AIOHTTP from BS4, import beautiful soup, import asyncio, ignore directories equals .well-known vscode, score pycac, images, The provided code is a comprehensive web application for visualizing NIFTI brain MRI data. It involves pre-processing NIFTI files, creating slices, saving volumetric data, and serving this data through a Flask web server. Additionally, it provides client-side JavaScript code for rendering 3D visualizations of the volumetric data using the 3JS library. Below are text instructions for another developer to rewrite it from scratch. Cache pre-processing script preprocess.py. The code provided is a comprehensive web application for visualizing NIFTI brain MRI data and can be divided into three main parts: pre-processing, server-side setup using Flask, and client-side visualization using JavaScript with 3JS. Here are the detailed instructions for another developer to rewrite it from scratch. Hashed pre-processing script preprocess.py. First, you need to import libraries such as Nibabel, NumPy, OS, Matplotlib, and JSON. Next, define a function that loads a NIFTI file using Nibobel, extracting and returning the header and data shape. Then, create another function to handle the creation of image slices and saving volumetric data. This function should load the NIFTI file, extract the data, and create output directories for axial, sagittal, and coronal slices, as well as volumetric data. The function should save slices in each orientation as PNG images using Matplotlib, and the volumetric data should be saved as a JSON file. Finally, in the main script execution, specify the NIFTI file path and output directory. Call the function to inspect the NIFTI file and print the header and data shape, and then call the function to create slices and volumetric data. Half-Flask application, app.py. Begin by importing necessary libraries such as Flask, SendFile, JSONify, RenderTemplate, and OS. Initialize a Flask app. Define routes, including one for the index page that renders an HTML template, another to serve individual slices based on orientation and index by checking the validity of the orientation and existence of the slice file, and a route to serve the volumetric JSON file. Optionally, define a sample route for serving additional volumetric data if needed. Finally, run the Flask app in debug mode. Client-side JavaScript, main.js. Set up a 3JS scene by initializing a scene, perspective camera, and WebGL renderer. Configure the renderer and attach it to a canvas element. Set up orbit controls for the camera. Load the volumetric data from the server by fetching the JSON file, parse the data, and create a buffer geometry object. Add the parsed volumetric data as points to the geometry, then create a points material and combine it with the geometry to create a points object, which is then added to the scene. Add ambient and directional lights to the scene. Position the camera appropriately to provide a good view of the data. Define an animate function to continuously render the scene and update controls. HTML template, index.html. Start with a basic HTML structure, including meta tags for character set, viewport, and SEO. Include external scripts for 3JS, Nifty Reader, and orbit controls. Create canvas elements for the 3D volumetric view and 2D slice views. Initialize a 3JS scene, camera, and renderer within a script. Load and parse the Nifty file using the Nifty Reader. Create a data texture 3D object from the parsed Nifty data and set up a shader material for ray casting through the 3D texture. Create a box geometry and apply the shader material to create a mesh, which is then added to the scene with camera controls configured. Add ambient and directional lighting. Define an animation loop to render the scene and update controls continuously. By following these detailed instructions, another developer can rewrite the provided web application from scratch, ensuring the functionality and structure remain consistent.